So here is the results when we train on a set of, I think I had 1,500 images I generated, and then we tested on something like 500, I think. So you can see that the ground truth over time is this white line, and then the predictions. So the predictions are relatively uniform, but there is some different spacing. So depending on what image we got, perhaps there wasn't very good lighting. The network didn't do so well. But overall, it looks like a very good fit. So that's great, but what are some of the, but of course this isn't a very realistic case. So let's talk a little bit about some more realistic considerations. One thing to consider is that spacecraft have very limited bandwidths and limited power. So while on the ground, it might be fun to take a video and just perform some type of neural network activity on that video. In space, it's much more difficult to get access to that video because it could be gigabytes in size. So we have to be very careful what images we select. Additionally, depending on when the satellite is over the ground station, we may only have a limited window in which we can access information. So we need to be a bit more strategic about which images we use. So yeah, those are the questions. How can our network perform with only limited images, and what's the best strategy for using these images? So here we have the same information again, but I'm showing it a bit differently. So we're estimating the pitch rate, the flat spin pitch rate, based on my pose estimations from each of those images. So we have 4 different methods here. So the first one is the dot, the white dot, and that's using all the points that are available. So if we had access to every image, and then we estimated the flat spin speed. So you see here that we get a flat spin speed of 1.004 degrees per second. Well, that's very good. The second method only uses 2 points, which are these little cyan circles here, the first and the last point. So because we have them spread out over such a large time period, we actually average out to get a very good estimate as well. The next method is the little pink squares here. So those, you can see we actually have 36 images. So theoretically we have more images than the cyan, and yet we have a slightly worse estimate. And that's because even though we have more images, they're taken over such a short period of time that we're not averaging out any potential errors between the images, or we are more sensitive to any error that our network has over a short period of time. And then finally, we have a pitch rate estimation if we take I think it's every 10 images here. So I summarize that here. We have the all points rate estimation, the 2 image rate estimation, the last 36 image rate estimation, and the every 120 seconds rate estimation. So you see, we get very good results. Is it? Oh, I'm sorry. There's one typo here. I forgot to change this 1004 to a 5, but that's okay. So you can see that the worst case is actually if we only use images over a short period at the end. But there's one more thing to consider as well, and that's in the bottom here. If we only took the first image and the last image, and we estimated the rate pitch from that, we can't tell if it rotated once, 10 times, or 100 times. And this is called we're undersampling the signal. We don't have enough information to know what the true shape of the signal is. So here's a nice little pictograph here. The true signal is this cyan signal, but if we took samples at such a low rate as we got these white dots, then we might assume that the signal looks like something else entirely. So this is something that's worth considering as well. So what is the optimal case? Well, I think the optimal case then would be to have images over a long period as much as possible, but also a relatively high sample rate for the last few images. So maybe an image every 10 minutes, and then in the last 10 minutes try to take an extra 20 images or something like that. I think that would result in a very good and accurate rate estimation. Another consideration is onboard processing. So right now we're talking about a post-processing where if we download images and we have all the time in the world to do things on the ground, that's great. But of course, what if we want the spacecraft to be making decisions on its own? So in that case, we want to have a neural network running on the spacecraft spacecraft itself. And unfortunately, it's just simply not feasible to load a convolutional neural network on current spacecraft hardware. For example, here's a summary of different neural networks that was from a paper in 2017. So ResNet 18 is not here, but ResNet 50 is. And you can see that it has over 100 million parameters and 50 layers. Okay, and here's an example FPGA that is quite a realistic thing to put on board a spacecraft. And this FPGA only has 19.1 megabytes of RAM. So when I try to train this on my laptop, I'm already up into 5 gigabytes. That's several orders of magnitude higher than an FPGA could handle. So we need to start considering how do we shrink these networks down. And there's a couple different solutions to that. One of them is called quantization, and that's actually currently what I'm working on these days. Is I'm looking how can I take a network which is working in, say, a floating point, 32-bit, 64-bit, and bring it down to 2-bit. So for each pixel, each image, like each pixel image in different layers, instead of having a value of 0.1 or 0.001, I say it's either -1, 0, or 1. And then what kind of accuracy and estimation can we get with that type of network? But it really reduces down the memory necessary. There's also, of course, we can simply use a smaller network, and there's lots of considerations with that. But in essence, that's what I'm working on right now. So again, thank you for your attention. I think that was a relatively simple case. In the next video, we'll go into working with real images. But I think that gave some great insight into how even a simple network can perform pose estimation. Thank you.